Hello, wonderful algebra students, and welcome to another lesson summary video. Our lesson we looked at today was called Graphs, Tables, and Equations, and the goal of this lesson was to recognize the connection between a linear equation, a graph representing it, and the coordinates of points on the graph. To get us started, the first part is really going to look at the connection between equations and the graphs representing those equations, which is what this first sentence says, right? There is going to be a connection between these equations, the graphs representing them, and specifically the coordinates, which is that pair of numbers that represent a point on the graph. To get us started and to help us with this conversation about the connections between equations in the graph, we've got the question number 1 here, where we're going to match these three equations to the graphs below. The three equations are y equals 2x minus 3, y equals 2x plus 3, and y equals negative 2x plus 3. This goes back to some of the work we had done in pre-algebra with linear equations and graphs. So I encourage you to go ahead, pause the video, and see if you can match those three equations now. And before I give those final answers, if you were stuck or just need a refresher of what we already know about equations and graphs, my one hint is going to be this. We had spent a lot of time talking about this formula here, slope-intercept form, where m represents the slope of a line and b represents the y-intercept. Maybe that jogs your brain a little bit. So if you have not already, again, pause the video, see if you can match these three equations. All right. There are a lot of different strategies you can use to help you match these three. My first strategy is going to be one of the things we had talked about with slope, is that slope tells you the direction of the line. So as I look at these three graphs down here, I notice both of these lines are going the same direction, but graph C is going a different direction. Graph C, that line is going down from left to right, which means graph C must be the equation that has a negative slope, and that is going to be this last equation here. I'm going to go ahead and say y equals negative 2x plus 3. That negative 2, remember we match it a lot of times with rise over run. It means each point, the next point is going to be down 2 and over 1. So if I'm starting right here, I can go down 2 boxes and over 1 box, and there's the next point on the line. Now for these two graphs, both of these have the same slope, that positive 2. I get that from the equation with the 2x. So both of those equations, if I'm starting here, I'm going up 2 boxes and over 1. Same thing over here. If I start here, for example, I go up 2 boxes over 1. Every single time up 2 boxes, up 2 boxes and over 1. The difference between these two equations is that y-intercept, which remember is what b represents. My first equation has a y-intercept at negative 3. My second equation has a y-intercept at positive 3. So when I'm looking at these two equations, I notice this graph right here intersects our y-axis at a positive 3, and graph B intersects our y-axis at a negative 3, which means when I go to match those equations, graph A is going to match with this middle equation here, y equals 2x plus 3, because it needs that positive y-intercept at positive 3, which means graph B is going to be y equals 2x minus 3. This is just a great way to warm up and refresh our minds about what we already know about graphs. Now, remember, we want to look at this connection between the equations, which are these three things right here, the graphs representing them, and then coordinates of points on the graph. So these follow-up questions are going to have to do with coordinates. Number 2, my first question is asking which graph is the point 2, 1 on. And when I'm looking at coordinates like these, remember that first number is always, always, always going to be your x value. I'll put it like this. And that second number is always, always, always going to be your y value. So that point 2, 1 is going to be the point at 2 on our x-axis and 1 on our y-axis. So for example, if I'm looking at this graph here, I would go to 2 on my x-axis and then also go up to 1 on my y-axis, which gives me this point right here. And it's asking me which graph is that point on. Well, I'm looking at that point, that purple point I just marked. That is not on the line. So that would mean the 0.21 is not going to be on graph A. It could be on graph B, it could be on graph C, it could be on both graph B and C. I'm going to have you go ahead and, again, pause the video to finish up question A. We said it's not graph A. Make sure you check graph B and graph C to see if it's on those. And then also try part B as well. Which graph is the 0.03 on? Go ahead, pause the video and do that now. All right, so for the 0.21, if I come to check graph B, 2 on my x-axis, 1 on my y-axis, I get this point right here. So I see it is on graph B. If I do that same thing over here for graph C, I notice that point is not on the line on graph C. So for this one here, I'm going to say graph B. When we go to check that 0.03, again, 0 is my x, 3 is my y. 0 is my x, which means I'm not going to move sideways at all. I'm just going to go up to 3 on my y-axis, which is right here. So I notice I see that point is on graph A. That point is not on graph B. And that point is also on graph C. So here I'm going to say graph A and graph C. The follow-up question to that is, when I was checking those points to see if they were on the graphs, I was looking at the graph, right? I was finding that coordinate point on our graph and checking to see, did that line run through it? Part C here is asking, how could we tell if a point is on the graph of the line using the equation instead of the graph? So notice when I was doing parts A and B, I was only using this graph. I wasn't paying attention at all to these equations. What if we only had the equation and not a graph? Could I figure out if this point was on, we figured out it was on graph B. How could I figure out this point was on graph B using this equation instead? If you feel like you already know, go ahead, pause the video and try it. What I want to remind us of is what we had talked about in the last lesson with solution points. What do you remember about our conversation about solution points? When we were checking to see if a point was a solution point for an equation, I think we summarized at the end of the lesson with, it's just a lot of substitution. I know if a number or a pair of numbers is a solution point to an equation, if when I substitute that pair of numbers into the equation, it satisfies the equation, meaning I get something that's true, like 3 equals 3 or 10 equals 10. That's going to come into play here as well. So if I wanted to check to see which graph the 0.21 is on, I could substitute those numbers in, and notice that where I'm substituting is right above it. I would substitute 2 for x and 1 for y, and check and see if it satisfies the equation. So for example, for graph A, I'll put my work right here under graph A. For graph A, if I substitute 2, 1 into this equation, y is the number 1, so it'll start off 1 equals, and then 2 times x, and x is going to be the number 2, so 2 times 2 plus 3. I know I don't even need to finish doing that math to tell that 2 times 2 plus 3 is not going to end up equaling 1. That's going to end up being 4 plus 3, which is 7. That does not satisfy the equation. When I go to do graph B, the equation is y equals 2x minus 3. Again, y is 1, so it'll say 1 equals 2 times x. My x coordinate is the number 2 minus 3. So I get something that says 1 equals 2 times 2 is 4, and 4 minus 3 is 1. So I see it does satisfy the equation. What do you think is going to happen over here for graph 3? Remember, we said the 0.21 is not on the line. What do you think I'm going to see when I do that substitution? Well, because I didn't say graph C was going to be an answer for this one, I'm guessing it's going to show that it doesn't satisfy the equation. Let's go ahead and do that math. we get 1 equals negative 2 times 2, which is negative 4 plus 3. And negative 4 plus 3 is negative 1. So again, I'm seeing that didn't work out. Go ahead and do something similar for 0.03 using that substitution we just did. And before you go ahead and start doing that math, make a prediction. What do you predict is going to happen when you substitute 0.3 into all three of these equations? Make that prediction and then go ahead and check your prediction by doing the math. Go ahead, pause the video now and do that. Alrighty. I'm going to do my math up here this time in green. My prediction is going to be, I noticed for part A, the only equation that was satisfied when I substituted the 0.21 in was graph B, was equation B, right? The other two didn't work. So for part B, I'm expecting to see that when I substitute this point in, it's going to satisfy the equation for A and C, and it's not going to satisfy the equation for B. That's my prediction. I'm going to go ahead and check my prediction. We're substituting the point 0.03. So y is 3. So it'll say 3 equals 2 times my x coordinate, which is 0, plus 3. 2 times 0 is 0, and 0 plus 3 is 3. So I've got it satisfies the equation in A. In B, it'll say 3 equals 2 times 0 minus 3. 2 times 0 is 0, and 0 minus 3 is negative 3. So I see it doesn't satisfy that equation. And then for this last one, y is still 3. So it'll say 3 equals negative 2 times my x coordinate, which is 0, plus 3. So we get 3 equals negative 2 times 0, which is 0, and 0 plus 3 is 3. So it satisfies it there again. So from these three questions, we can come to this conclusion. Remember, we're trying to figure out what the connection is between the equation, the graph, and these coordinate points. And what I'm seeing is for a point like 2, 1, I can tell from the graph by finding that point on the graph and seeing if the line goes through it, or I can check to see if that point is on the line by using what we know about solutions. I can check to see if this point is on the line using the equation and checking to see does it satisfy the equation when we substitute in that point. So to summarize what we're seeing here, you can tell if a coordinate is a solution to a linear equation using the graph or an equation. So it's going back to our conversation about solutions. In an earlier lesson, we saw that a coordinate is a solution if, when substituted into the equation, it results in a true statement. So that's that math we're doing right here. So if I asked you if the point 0.03 is a solution point, you can check that by seeing, well, is 0.3 on the line? Or you can check and see, does the point 0.3 satisfy the equation? So we can use substitution, or you can check a coordinate is a solution to an equation if, when that equation is graphed, the point lies on the line. So we get these different mathematical representations, graphs and equations. They both have their own advantage when it comes to seeing if a point is going to be a solution point. Coming down to these last two questions we've got, I've got these same three graphs from above. I've just copied them below, so we don't have to keep scrolling up and down. And we're really going to focus in on graph B for these last questions. So for number 3, it's asking us name a solution point for the equation in graph B and confirm that this is a solution point using both the equation and the graph. So we've got the graph right here, and to help us out, I'm going to copy that equation as well. The equation, remember from earlier, was y equals 2x minus 3. So go ahead for number 3 and do exactly what it's asking. See if you can identify a solution point from this graph, and then confirm how, whatever that point is you pick, and remember your point's going to have two numbers on it, an x and a y. Confirm that that point is a solution using the graph, and confirm that that point is a solution using this equation. Go ahead, pause the video, and try that now. All right. So for number 3, you might have thought of the point 2, 1. After all, that is the point from a moment ago that we have already identified as a solution point using both the graph and the equation. I can scroll up just to remind us. Remember 2, 1, we said as a solution point because it lies on the line. And right here, when we substitute it, we saw that it satisfies the equation and gives us a true statement. However, is that the only point you could have picked? No. Using what we just said, solution points are points that lie on the line and satisfy the equation. There are many more points you can use as your solution point for number 3. Solution points are these points that lie on the line, right? Well, if I look at my line here, I can find a lot more points that are easy to identify the coordinates for, like this point right here. Because that point's crossing those graph lines exactly, I can see that the coordinate 3, 3 could be another solution we list. I got 3, 3 using the graph. I used the graph to find a point that lies on the line. But remember, I can confirm it using this equation as well. If I substitute 3, 3 into my equation, y is 3, x is also 3, I can see that it gives me a true statement. It satisfies the equation. Now, is 3, 3 the only other point you could give? No, of course not. There are a lot more points on this line. So you could have said 4, 5. You could have said 1, -1, 0, -3, -1, -5. Now, are those points I just listed and marked on the line the only points you could use? Again, no. I'm picking these points here that I mentioned earlier that are easy to identify, but those are not the only points on the line, right? This point here, even though it's not going through those perfect graph lines, that still would be a solution point. It looks like it might be 3.54. It can be hard sometimes estimating what those decimals are. It looks like 3.5, but it might be 3.49. It might be 3.6. However, that's why we have this equation, and we could confirm it using that equation. It is 3.5, I believe, 3.54. But if I didn't know that, I could confirm that in the equation. In addition to all those fun decimal points, remember this line doesn't end here. Sometimes we mark it with these little arrows to remind us that line goes on forever in both directions. So there would be more points on either side of where my graph stops that I could use as well. There are tons and tons and tons of points you could have given me for 3. And the way to confirm is just by seeing that that point is on our graphed line and satisfies our equation when we substitute in those numbers. See, we keep coming back to the substitution, and now we're also including this idea of it being on the graphed line. Number 4 is kind of the opposite. So still looking at graph B, can you name a point that is not a solution for the equation? How do you know it's not a solution using the graph? How do you know it's not a solution using the equation? Go ahead, pause the video, and think through question 4 on your own first. So number 4, we'd mentioned, is like the opposite of number 3, which means I need the opposite statement of what we said in number 3. Number 3, we said it's a solution point if it lies on the line or satisfies the equation. The opposite of that would be it's not a solution point if it does not lie on the line and does not satisfy the equation. So for example, I'm going to use red. For example, when I look at my graph, I see the point 5, 1. That point is not on the line. So I'm anticipating that not being a solution point. I could check that by using substitution, but this time, since I don't want it to be a solution, it means I don't want it to satisfy the equation. I don't want it to work out. So I chose 5, 1, and I just chose that at random. You could choose any point not on the line. If I substitute 5, 1 into our equation, remember our equation is y equals 2x minus 3. My y is the number 1, and then my x is the number 5. So I get 1 equals 10 minus 3, 1 equals 7, which does not satisfy the equation. So when we're talking about solutions, to summarize here, it's a solution if that point lies on the line and satisfies the equation. It's not a solution if that point does not lie on the line and does not satisfy the equation. The other thing we're noticing here, especially from number 3, is we said that there are lots and lots and lots of solution points for these linear equations. The same thing would be true for graphs A and graph C. The mathematical word we use for that, and I'll scroll back down, is infinite. There are infinitely many solutions, which means there's so many solutions I can't count them. Remember we said earlier, yes, like all these points I marked are solution points, but there's points in between those points that are solutions. And then because that line continues, there are points going on forever and ever in both directions as well. So we say that there are infinitely many solutions. There's an infinite number of coordinates on the graph line that, when substituted, result in a true equation. That does not mean that everything is a solution point. Notice we saw here 5, 1 is not a solution point. It just means that there are an infinite number of coordinates that would be solutions. Now, the last part of this lesson review, when we're talking about solutions and solution points, it can be a little abstract, which is why our final part here is looking at a real life situation. And I find that for a lot of students, this kind of helps make this idea of a point being a solution point all make sense. So for this last part here, we've got an equation, a graph, a table, all below that show Octavia's running speed in terms of how many miles she can run. And for miles, we're using y, and a certain amount of minutes. And for the number of minutes, we're using x. So I've got this equation, I've got this graph, and then we're also adding in a table here as well. Our first question we've got is, if x equals the number 10, what does y equal? And to answer that question, there is a way for you to use each of these mathematical models, each of these representations. There's a way for you to figure out what y equals using the equation, using the graph, and using this table. I'm going to have you go ahead, pause the video, and see if you can work out first what y equals using whichever model you would like, and then see how you could confirm it with the other two. Go ahead and do that now. For me personally, if I'm trying to figure out what y equals, I notice right away my table actually has x equals 10 in it. Remember minutes, that's our x, and miles is our y. So not everything's going to be listed in my table because there's limited space in a table, but I do know that x equals 10 is listed, which means right here I'm given what y is. I've got y equals the number 1. I'm going to go ahead and write that down for us. Now, you might have started with a different one, but remember we had said there's a way to figure out y equals 1 from all 3 of these representations. If x is the number 10 and I wanted to figure out what y is using my equation instead, guess what we need to do? Yes, you were right. It's our favorite thing, substitution. So I could take my equation y equals 0.1x, and we're told x is the number 10. So I could go ahead and substitute or replace x with the number, not 1, x with the number 10, and then do that math to figure out what y is. When you multiply 0.1 times 10, you get the number 1. So I could use substitution with my equation to figure out what y is. Or what about this graph here? If I know x is the number 10, how could I figure out what y is from this graph here? Well, if x is the number 10, I would want to find 10 on my x-axis and then go up to my line to see where the y coordinate would be. I'm going to zoom in on our graph a little bit for this. Now, this graph makes it a little challenging because notice 10 isn't labeled down here. This line right here is halfway between 0 and 30, so I know that line is 15, but I'm trying to find 10. So 10 would be like a little before it, maybe around like right here. So it is challenging when you're trying to find that coordinate we talked about earlier, those exact points on our graph line. It's hard when it's not going to be an exact point on your graph line. But the process would be the same no matter what. I would find 10 on my x-axis and then go up to my line. So it looks like the point would be right here. So I'm seeing when x is the number 10, and let me write in that 10 as well. Ooh, with a very large 10. We're seeing when x is the number 10, we've got y is the number 1. So I'm going to 10, going up to my line, and then going over to see what that y value is. If I was asking for an easier number, maybe I was asking you about 120, the process would be the same. If I wanted to know what y is when x is 120, I go to 120, I track 120 up to my line to find that coordinate point, which would be right here. And then I'm going to come over to see, well, that's the point where x is 120. What's the y? And the y would be 12. So it's finding those points on the line, which has been a big theme today as well. Let me erase this. I have one other question for you regarding this pair of numbers. So we figured out if x is 10, y is 1. But what do those numbers mean in the story? We've got a 10 and a 1, and I'll scroll up a little bit so you can see that story again. What does 10 and 1 mean? Remember, x is the number of minutes and y is our miles. So if x is 10, that means in 10 minutes, Octavia can run 1 mile. If we look at our table, we're lucky our table already has those labels there, and we can confirm as well. It takes 10 minutes for her to run 1 mile, which in my opinion is pretty good. I've got another similar one for that. Definitely this one I want you to try on your own. Number 2 says, if y is 2.5, what does x equal? And we've got those same two questions here. How could you use each of those representations above to figure out x? And then what does that pair of numbers represent in the story? I am going to scroll up so you can see those 3 representations. Remember, we've got y is 2.5. So I'll put that up here in blue for us. We are trying to figure out if y is 2.5, what is x, using all 3 of these representations. Go ahead, pause the video now, see if you can figure out what x is using all 3, and then what that pair of numbers would tell us. All right. If I go in the same order we had done the first one in, if I'm using my table, again, I am lucky enough that y equals 2.5 is in this table. That's not always going to be the case, but here it is. Remember, we're given y this time, so I'm going to go to that y column. I see y equals 2.5 right here, which means that our x value is going to be 25. I can confirm that using our equation and our graph. On our graph, y equals 2.5. This time because we're talking about y, I'm going to go to my y-axis. 2.5 is going to be in the middle right here. So I'm going to track it over to our line and then down. It is hard to estimate that since we're not given an exact number. But remember, I'm just trying to confirm using these other 2. So I would believe that that would be around 25. That equation, though, is going to be much more precise if we're trying to confirm that. With our equation, this time we're given y, so I want to substitute for y. It's going to be 2.5 equals 0.1x. This one's a little different. I have to figure out what x is, which means I want to solve for x. I'm going to do that. Since 0.1x is 0.1 times x, I'm going to do the opposite, which is dividing by 0.1. And if I divide both sides by 0.1, I get 25 equals x. So we've got three very different representations: a table, an equation, and a graph. But what all three of these have in common is that they show you solutions to the situation. All three of these can be used to help find solutions to the situation, which in this situation, this pair of numbers is telling me it would take her 25 minutes to run 2.5 miles. A table is just a list of solution points. A graphed line is just like a visual of all those solution points. Any point on the line would be a solution point. And then an equation doesn't tell you any one solution the way a table and a graph do, but an equation can be used to find any solution point. So maybe Octavia decides tomorrow morning that she wants to run for 30 minutes. My table's not going to show that, but I could substitute 30 for my number of minutes using this equation to figure out how many miles she can go. Another example could be if we knew she was running 120 minutes. We had used that one earlier. 120 minutes isn't in my table, but it is really nicely on my graph. I could come over to my graph and see 120 minutes. It's going to take her 12 miles. And that graph might be the most helpful thing where I don't have to do any calculations. Or maybe she runs 63 minutes. I could do the calculation. The graph's going to be really challenging because it's not exact, but you know where 63 minutes happens to be? In our table. So they all have their own benefit. So to summarize this last part, rows and tables and points on lines both represent solutions to that equation, that related linear equations. Tables, equations, and graphs are all different mathematical representations to show those numerous solutions we talked about earlier in this particular situation. This concept here is one that we're going to build on as we continue throughout this unit, but this, I think, gives us a really good summary of some stuff we had learned back in pre-algebra with graphs, tables, and equations, and helps reinforce the stuff we learned about solution points in yesterday's lesson. Thanks so much for watching. I hope you found this helpful, and I will see you back tomorrow. Bye, y'all.